Hi, this is Tzvi Rosen back with another lecture in our series on the history of calculus. And today's lecture will focus on one of the all-time greats, Augustin-Louis Cauchy. And just as a way to kind of set the stage, Cauchy lived in a very tumultuous time in French history. He was born in 1789 and he died in 1857. And you can see at the left a timeline of who was ruling France from before 1792 until after 1870. And you can see power was changing hands every couple of decades. So Cauchy was born into the reign of Louis XVI and lived through the French Revolution, the First Republic, the rise of Napoleon, the French Empire, and just more and more tumultuous politics. And it affected his research. It affected where he chose to live. It affected the kind of scientific community he was developing in. And let's go into his life a bit. So he was born, as I mentioned, in Paris in 1789. His father was a government official, and as a government official, he was connected to other prominent mathematicians. We've seen Laplace and Lagrange. During the Reign of Terror, Cauchy's family escaped, leaving Paris to one of the surrounding towns, and then they returned after the execution of Robespierre. When our hero, Augustin-Louis Cauchy, Cauchy Jr., grew up, he worked as an engineer, participating in the building of the harbor of Cherbourg during Napoleon's rule. But he got bored of engineering at a certain point and started doing math while on the government payroll. So he was able to maintain his occupation with the government. After Napoleon was defeated and there was the Bourbon Restoration, Louis XVIII purged two of his political opponents, Carnot and Monge, from the Academy of Sciences and appointed Cauchy instead. That made Cauchy a very unpopular person with other mathematicians in France. And who knows, perhaps because he was so unpopular, it led to him being willing to challenge orthodoxies in the mathematical world. Cauchy became a math professor at the École Polytechnique in 1815. But then in 1830, the July Revolution exiled Charles X, who was king at the time, and began a constitutional monarchy under Louis Philippe. But Cauchy was not sympathetic to the new government. He viewed the violence that accompanied their rise to power as illegitimate, and he felt politically alienated. So he left his family in Paris and went into exile, first in Turin, which is in Italy, and then in Prague for a longer period of time. He eventually returned to Paris in 1838, but the government at the time was requiring anyone who would occupy a professorship to take an oath of loyalty to the government. And Cauchy refused to do that, so he was excluded from occupying a professorship. But then the revolution of 1848 happened, and a different government came into power, and they gave Cauchy an exception to loyalty oaths, and he was reinstated in 1849. And he continued in his academic life in Paris until 1857 when he passed. Okay, so clearly a very turbulent life, but one that was incredibly productive and impactful in mathematics. His mathematical contributions, first and foremost, which we'll be discussing today, he established rigorous foundations for calculus and founded the field of modern analysis. He also proved some of the first major results in complex analysis, which studies functions of complex variables. So variables that can take values including the square root of -1. And there are a couple of important ideas in that field named after him: the Cauchy-Riemann equations and Cauchy's integral theorem. He also did one of the early theorems of group theory in modern algebra. Cauchy's theorem says that if a prime number p divides the order of a group, then the group has an element of order p. And it's not a trivial result. He also made contributions in linear algebra. For example, the Cauchy-Schwarz inequality, which is related to inner products of vectors, as illustrated here, as well as the Cauchy-Binet formula for determinants. Okay, so let's explore Cauchy's impact on the calculus. And we'll recall that there was a period of backlash to the calculus, starting with Berkeley's critiques, and people were questioning the foundations on which calculus was based. And enters Cauchy to define the limit. So I know we would hope that he would have written something involving epsilons and deltas, but it wasn't quite so clear as that, even though the ideas are buried in there. So his definition of limit was as follows. When the values successively attributed to a variable approach indefinitely to a fixed value in a manner so as to end by differing from it by as little as one wishes, this last is called the limit of the others. Okay, so let's kind of unpack that a little bit. So we have values successively attributed to a variable. Okay, so I'm writing down a sequence of values that would be assigned to, let's say, the variable x. Okay, and they approach indefinitely to a fixed value. So let's take a fixed value L. In a manner so as to end by differing from it by as little as one wishes. So let's take as little as one wishes to mean for any epsilon greater than 0. Okay, so you should be able to name any positive tiny quantity, and then for all n greater than some capital N, we want xn minus L to be less than epsilon. Okay? So then under this condition, L is called the limit. Okay. And if we wanted to draw this pictorially, we might have a progression of values all approaching some fixed value, getting arbitrarily close to it. Okay. But key here is the idea that we don't need to be arriving at the value. We just need to be as close as we want. Okay, so there's an implicit notion of inequality here. Okay, there's a note, inequality, meaning we're staying as close as desired without requiring some kind of equality, like we actually reach this L. Okay. And this was a revolutionary idea, and it's kind of it's a response to Berkeley's accusations that we have these infinitesimals that are sometimes 0 and sometimes not 0. Cauchy's response is, no, we don't have infinitesimals. We just have quantities that are getting as small as desired. Okay, they're staying below arbitrary bounds. And using those inequalities, we can define our limit. Okay, and yet even though he makes this very subtle definition of a limit, then he starts talking about quantities that are infinitely small. But we can kind of spell out what he means. So he defines continuity and derivatives. First, we'll see the definition of continuity, we say y equals f of x is continuous if for I infinitely small, delta y equals f of x plus I minus f of x is also infinitely small. Okay, so to formulate this in more quantifier and inequality-friendly terms, so for I infinitely small, so we want delta y to be infinitely small. So for arbitrarily small epsilon, okay, we need to be able to find a delta such that I less than delta implies delta y less than epsilon. Okay? So that's how you can finesse his words to look more like the modern formulation of continuity. As for his definition of the derivative, if we have a function y equals f of x and I infinitely small, define the derivative delta y over delta x equals f of x plus I minus f of x over I. Okay, again, I infinitely small is a problem, but we just take this to be a limit. Okay, and it's clear that this is what is meant from his writing. So limit as I approaches 0 of f of x plus I minus f of x over I. Okay, so, and there's no issue having I equals 0 even, or having I approach 0, because we're not actually dividing by 0, we're dividing by arbitrarily small quantities, okay, and seeing how this ratio changes as those quantities get closer and closer to 0. Okay, so now that Cauchy had set up the limit and the definitions of continuity and derivatives on much more rigorous grounds, he was able to prove some important theorems. And the first that we'll look at is the intermediate value theorem. And the theorem goes, suppose f of x is a continuous function on the interval a, b, then f of x takes all values between f of a and f of b. Okay, and a quick example of this is if you have the function e to the x minus 2, so let's get a graph here. Okay, so if we want to graph the function e to the x minus 2, so when x equals 0, we have minus 1. And at x equals 1, it's closer to 0.7. Okay, and then everything else is just a shifted exponential curve. So on the interval between 0 and 1, there must exist some value x. Okay, so there is an x in the interval 0, 1 such that e to the x minus 2 equals 0. Why is that? Because f of 0 is minus 1, and f of 1 is e minus 2, which is about 0.7, 1/8, dot, dot, dot. So our function has to take every value in between those, one of which is 0. Okay. So this implies that there exists a real number, ln of 2. Okay, so that's one way to use the intermediate value theorem. Now let's look at the proof. Cauchy's idea was basically as follows. We start with our interval a, b, and we know that, it's enough to just prove that we get, if we're negative on one side and positive on the other side, then somewhere in the middle, we're going to get 0. So we want to find the 0, x, such that f of x equals 0. Okay? And his idea is to continuously divide, or not continuously, to repeatedly divide up this interval until we zoom in on where the 0 must be. And so let's pick some number. So divide interval into m subintervals. Okay. For our example, we'll take m equals 4. Okay, so we're going to split up to 4 equal subintervals. Okay, and then you look for what the sign at each of your subinterval division points is. Okay, so here the function is still negative, here it's positive, sorry, here it's still negative, and here it's just turned positive. Okay, so that tells us to make a new point. So this will be our x1, and this will be our capital X1. Okay, lowercase and capital. Okay, and so now taking that new interval, x1 to x1, we're going to divide that again into 4 intervals. Okay, so we have 1, 2, 3. And here, we're going to find what the signs of f of x is at each of the division points as before. So here it's still negative, here it's still negative, here it's still negative, and here it's still positive. It becomes positive. So we get, this will be our new x2, and this will be our capital X2. Again, the points that we're choosing for lowercase x is the last point where it's negative, and then the capital X is where it switches over to positive. Okay? And so then we would do the same thing again, splitting it up into 4. So we have 1, 2, 3, and we would determine what are the signs of each of these, of the function at each of these points, and then pick our next points based on that. So this allows us to construct sequences x1 less than or equal to x2 less than or equal to x3, etc., and x1 greater than or equal to x2 greater than or equal to x3, etc., where the distance between these two x's, so xk minus capital Xk, is always going to be less than or equal to the distance between b and a divided by m to the k. Okay, because we're splitting it, we're repeatedly, iteratively splitting up this interval into m subintervals, so we get m to the k each time. So these xk and capital Xk and lowercase xk are getting closer and closer. So we could take the sequence lowercase x1, capital X1, lowercase x2, capital X2, etc., and we can see that the terms of the sequence are getting closer and closer to one another as we go along. So this is called a Cauchy sequence. Okay, and in technical terms, this is a sequence where for any fixed epsilon greater than 0, so you want things to be very close to each other, there exists some capital N such that for any m and n greater than capital N, let's call the general term of this sequence y, ym minus yn is less than epsilon. Okay, and the assertion is that Cauchy sequences converge to a limit. Okay? So, we should note this is not true in general. Okay, it's not true that depending on the domain you're working in, Cauchy sequences don't necessarily converge. That's a property called completeness. So, fortunately, the reals are constructed to have the property of completeness, so we know that Cauchy's assertion is true, but it does rely on an unstated axiom, which is completeness of the reals. Okay, so let's call this limit that this converges to L. Okay, so let's consider how the function that we're working with acts on L. Okay, what's the value of f at L? So we know that for the sequence lowercase x1, lowercase x2, lowercase x3, etc., f of x1, f of xk really, is less than or equal to 0 for all k. Okay, what that implies, sorry, it's actually strictly less than 0 for all k. What that implies is that the limit, well, let's put it this way, f of the limit as k goes to infinity of lowercase xk is the limit as k goes to infinity of f of xk. This is by continuity. So that implies that f of the limit as k goes to infinity of xk, which is just f of L, must be less than or equal to 0. Okay, similarly, and that's straightforward. You can't have a sequence of negative numbers that approach a positive limit. They could approach 0, or they could approach some negative limit. If you have the capital letters x1, x2, x3, etc., where we know that f of xk is greater than or equal, it's strictly greater than 0 for all k, then f of L, which is the limit, the f of the limit as k goes to infinity of xk, will be equal to the limit as k goes to infinity of f of xk by continuity yet again. And that means that f of L must be greater than or equal to 0. Okay, and since we have from each of these implications, f of L is both less than or equal to 0 and greater than or equal to 0, that tells us that f of L equals 0. Okay? And to show that it would take any intermediate value, all you have to do is shift your function so that whatever value you want it to take, just subtract that. and then you're talking about the function taking the value 0. Okay, so we've seen Cauchy's proof of the intermediate value theorem. There are unstated assumptions. In particular, completeness of the reals, but still, this is a very sophisticated and modern proof. Okay. Now let's look at another theorem of Cauchy's. This one is the mean value theorem. And here's how Cauchy stated it, though it's different than the way you'll find it in modern textbooks. Suppose f of x and its derivative f prime of x are continuous on the interval x0 to x. Then there is a theta in the interval 0, 1, such that f of capital X minus f of x0 divided by x minus x0 is equal to the derivative of f evaluated at x0 plus theta times x minus x0. Okay, the way this is generally described is not using this theta. This just means some point between x0 and x. Okay, but this is the way that Cauchy presented it. So what does this mean as far as a concrete example? Let's consider the function sine x. Okay, so we have, let's take our interval to be 0 to pi over 2. Okay, and we have pi over here. The sine function basically looks like this, that we have a peak at x equals pi over 2, where this takes the value 1. And it goes from 0 at x equals 0 to 0 at x equals pi. So, what does the mean value theorem say? That if I look at this slope, where I start at x equals 0, and I go to the end of the interval, start at one end of the interval, go to the other end, the slope of this line, okay, so if we call this, for example, L, the mean value theorem says that there is some point x in the interval 0 to pi over 2 such that f prime of x is equal to the slope of the line L, which you can compute easily is 2 over pi. Right? Rise of 1 over run of pi over 2. Okay, so that's what the mean value theorem tells us. And we'll go into part of Cauchy's proof. So a big part is from this lemma, which is proven in the calculus gallery according to how Cauchy did it, that if you have a continuous function on the interval x0 to x, and you set a to be the minimum value that the derivative takes, and b to be its maximum value, then this slope function, f of capital X minus f of x0, divided by capital X minus x0, will be bounded between a and b. So there are important notes to keep in mind here, important caveats. So it's not in general true that you have these bounds. that f prime achieves its maximum and minimum. And strictly speaking, you don't need that to make a proof of the mean value theorem work. But for Cauchy's proof, this ratio is this is very useful. So we'll just add that as a hypothesis that the derivative is bounded on our interval. Okay, so let's add that hypothesis so that Cauchy's proof works. Okay. We'll use this inequality to prove the mean value theorem. So taking this inequality, we have A and B are bounds for this ratio. But by our hypotheses, we know that f prime is a continuous function. So it's going to take every value between its maximum and minimum. Okay, that's true by the intermediate value theorem. F prime takes every value between its min and max, which are A and B. And that's basically it. So taking, so that means there exists an x, which we can call x naught plus theta times x minus x naught for theta in 0, 1, such that f prime of x is equal to this ratio f of capital X minus f of x naught divided by x minus x naught. So that proves the mean value theorem. So Cauchy's strategy was to prove this lemma of inequalities about the ratio f of x minus f of x naught over x minus x naught, as we saw, and he does that using a subdivision strategy together with some tricks related to inequalities and how you can combine them, and then simply using the intermediate value theorem for f prime. But some remarks here are important. So Cauchy's proof assumes uniform continuity of the derivative. But it's actually true that the mean value theorem holds even if f prime is not continuous at all. And you might say, well, how would you contrive of a derivative that isn't continuous? Here's an example. So we have f of x is equal to x squared sine 1 over x whenever x is non-zero, but it's 0 when x is equal to 0. So you can check that f prime exists everywhere. So away from x, you have, away from x equals 0, f prime of x is just the derivative of this smooth function x squared sine of 1 over x. So that's 2x sine 1 over x plus x squared cos 1 over x times minus 1 over x squared. And this is true when x is not equal to 0. And when x equals 0, we have the limit as h approaches 0 of f of 0 plus h, just h minus f of 0 divided by h. So this is equal to the limit as h approaches 0 of f of h over h, so that's h squared sine 1 over h divided by h, which is the limit as h goes to 0 of h sine 1 over h. Okay, so the sine term oscillates wildly, but h is drawing it to 0, so this derivative does exist, and it equals 0. However, it's not continuous at 0. And you can check that by seeing what the limit of the first expression is as x approaches 0. And this is evident based on the second term of the derivative, the cosine 1 over x. Since the x squareds cancel, you have this wild oscillation as you approach x equals 0. However, even though not all derivatives are continuous, all derivatives satisfy the intermediate value theorem. And this is a theorem proved later on by Darboux. So Cauchy's version of the mean value theorem, while being amazing and being a revolution, is still not quite the modern one that we have today. Now let's look at another contribution of Cauchy's. He gave a new definition of the integral. So the definitions given previously were never formally defined in terms of a limit. They're just kind of heuristically described as the area under a curve. And Cauchy gave a rigorous definition. So we'll consider a function f of x on an interval ab. Then we'll subdivide ab into a sequence of points x0 through xn, so that the lengths of the intervals between xk and xk minus 1 become arbitrarily small. And we'll define a sum, an approximating sum, s sub n, as x1 minus x0 times f of x0 plus x2 minus x1 times f of x1 plus up to xn minus 1 times f of xn minus 1. Okay, so just to clarify what's happening here, we have this graph So let's say our function looks like this. Then what's being described here is left-hand sums. Okay, so you take the width of a subinterval and you multiply it by the height, meaning the function value at the left endpoint. Sorry, that should be here. That gives you the left-hand sum that you might have encountered in a standard Intro to Calculus course. Okay, so what Cauchy says is that if the limit of these Sn exists independent of your choice of subdivision, so that no matter how you choose these intermediate points, you always get to the same limit, then you define the integral to be that limit, okay, where the number of subintervals approaches infinity, and the length of the subintervals becomes arbitrarily small. If not, then our function is not integrable. Integration doesn't apply to it. Okay, now that he defined his integral, Cauchy was able to prove the fundamental theorem of calculus. And the way he stated it is that if you have a function capital F with a derivative lowercase f, then the derivative of the integral from x naught to x of f of x dx equals f of x, and the integral from x naught to capital X of f of x dx equals capital F of x, capital X minus capital F of x naught. So we can forgive him for using all these different forms of x, but something we wouldn't really forgive in a modern context is using the same variable to integrate against as well as in the bounds. So modern notation would have something like d dx of integral x naught to x of f of t dt. Okay, but Cauchy was doing this with no precedent, so we'll forgive him for abusing notation in this way. So this was his form of the fundamental theorem of calculus. Okay, and to prove the first direction, the first aspect of the fundamental theorem of calculus, so that the derivative of an integral is the original function. So we need the following lemma, which is a form of the mean value theorem for integrals, that if we have f of x a continuous function on x naught to x, then there's a theta in the interval 0 to 1, such that the integral of f of x dx from x naught to capital X is equal to capital X minus x naught times f of x naught plus theta capital X minus x naught. The proof of this is rather similar to the proof we saw for the normal mean value theorem. The key idea here is to notice that using the Cauchy's definition for an integral, so if you take any Sn, so for example, xk minus xk minus 1 times f of x k. Okay, we'll take k to be from 0 to n, or I guess from 1 to n. Okay, well, what if so we can describe f as having an upper bound and a lower bound. Okay, so it's a continuous function on a closed interval, so that's, well, he didn't necessarily put it that way. We know that on compact sets, f attains minimum and maximum. So we can let a equal the min of f on the interval x naught to x, and we can let b be the max of f on x naught to x. Okay, then this is going to be greater than, so replacing f of xk by a throughout the sum, and then we can factor out the a, and what's left is just the sum of all the intervals, so that's just the length of the interval. So this is going to be a times capital X minus x naught, and as an upper bound, b times capital X minus x naught. Okay? Now we can take this inequality to the limit. Okay, the left hand and right hand aren't affected, only the middle is. At the limit, we have a times capital X minus x naught less than or equal to the integral x naught to x of f of x dx less than or equal to b times capital X minus x naught. Okay. Dividing through by x minus x naught, we get a less than or equal to x naught to x of f of x dx less than or equal to b, need a denominator here. Okay, so now we have this value is between a and b. And we know f takes the values a and b, so f must also take this value by the intermediate value theorem. Okay, so by the intermediate value theorem, there is some value, let's call it y, in the interval x naught to x, such that f of y equals this integral x naught to capital X of f of x dx divided by capital X minus x naught. Okay? And multiplying through again, we get x minus x naught times f of y is equal to x naught to x of f of x dx. Okay, and that's enough to prove the lemma, the mean value theorem for integrals. Okay, so how do we use it to prove the fundamental theorem? Let's compute the derivative as a limit. So we have d dx integral from x naught to x of f of x dx. This is going to be the limit as h goes to 0 of integral from x naught to x plus h f of x dx minus integral from x naught to x of f of x dx all over h. Okay. So using the definition in terms of these left-hand sums and making sure that x is one of the endpoints in your intervals, this is going to be the limit as h goes to 0 of the integral x to x plus h f of x dx, and we'll have a 1 over h out in front. Okay, all this is observing is that you're throwing away any rectangles that come before x while holding on to the rectangles between x and x plus h. And at this point, we can use the mean value theorem that we proved. We have limit as h goes to 0 of 1 over h times h f of x plus theta h. Okay. But here we see the h's cancel, and we're left with the limit as h goes to 0 of f of x plus theta h, which is f of x. Okay? So that proves part 1 of the fundamental theorem. How do we prove? So let's give a little square. Now let's try and prove part 2. Okay, so we're going to name this. Let's state part 2. We want to know that taking the integral of f of x dx from x naught to x equals capital F of x minus capital F of x naught. So what we're going to do is take phi of x. This is going to be a new function for us, and we're going to use it to define x naught to x f of x dx. Okay, so this variable is appearing in the upper bound. It's saying whatever x value you're giving, do the integral from x naught to that new x value. Okay, and so we just saw from the first part. Okay, so we're going to let this be true. This is the statement we want to prove. So we have phi prime of x is going to be f of x. But by the hypotheses, we already know that capital F of x prime is also f of x. So this tells us that the function phi of x minus f of x, since its derivative will be 0, it's just f of x minus f of x, this has to be a constant function. Okay, and all we have left to do is figure out what c is. And we can do that by plugging in x equals x naught. What do we get? We get phi of x naught, okay, which we know to be 0. So we're left with minus f of x naught equals c. Okay, So that tells us what C is. So in particular, we have phi of x equals capital F of x minus f of x naught. Okay? And now, having done that, we can plug in x equals uppercase x, and we get phi of uppercase x, which we know is integral from x naught to capital X of f of x dx, has to be capital F of capital X minus capital F of lowercase x naught. And that proves our theorem. So Cauchy, if you've taken a modern analysis course or even some advanced calculus courses, all of this is stuff that we do in those courses because Cauchy really laid the groundwork for what is the modern rigorous development of calculus. Let's summarize what we saw. Berkeley, I should say, as we saw in the last lecture, challenged mathematicians to deduce our conclusions from principles, not vice versa, not just you find a tool that works and then allow that to define, to retroactively make up our principles. And Cauchy responded by defining limits rigorously, and then he gave rigorous definitions of continuity, derivatives, and integrals. The key concept in his mathematical reasoning was inequalities. When you have quantities staying below arbitrary bounds, that can be thought of as equivalent to approaching zero or reaching some limit. Cauchy's definitions rigorized the theorems of calculus. And Cauchy took a quantum leap towards the modern calculus, but tinkering was still necessary. As we saw, there were still bits and pieces of the theorems that were not quite at the modern version, assumptions he made that weren't necessary, assumptions he forgot to make, like completeness of the reals. And that should be a lesson about the history of math, that we're always iteratively getting towards a complete development. You know, ideas don't take their final form right away. You need conversation and the collaboration of the mathematical community to fine-tune these things until they are in their best possible form. But it's still, even though you need that collaboration, you can't deny that Cauchy was just a transformative figure who took calculus from this really neat tool that nobody really got why it worked to a discipline unto itself. Okay, thanks for your attention.